Hello students, welcome back. We just completed section 1 of this notebook. Let's go to section 2, inverse functions. But first, let's establish the concept of one-to-one functions. A function f of x is said to be one-to-one if it's a function and each output comes from one and only one input, like the first picture here. The second picture here is not one-to-one. It's a function. Each input is sent to one and only one output. x1 is going to y1, x2 is going to y1, x3 is going to y3. Each x value is going to only one y value, so it's a function, but not vice versa. The third one is not a function. x1 is assigned to y1 and both y2, so this input x1 is being assigned to more than one output, so it's not a function. B is a function, but it's not one-to-one. A, it's a one-to-one function. It's a function. Each input is going to one and only one output, and also each output is coming from one and only one input. That's one-to-one function. There's an easy way to test a one-to-one function if you have a graph of a function, and that's horizontal line test. Remember the vertical line test for functions. Vertical line must cross the graph only once, otherwise it's not a graph of function. Similarly, we can do horizontally, and here they're all graphs of functions. As you can see, they all pass vertical line tests, but only the middle graph is one-to-one function. I'm changing the horizontal lines, and each time we have only one crossing for the middle graph, but here I have sometimes one crossing, but sometimes I have three crossings like this. And here in general, I have multiple crossings. What do you mean by that? Each y-coordinate here, the output, has only one crossing, so it's coming from only one x-coordinate, the input. Here we have three crossings, so each y-coordinate here, this particular y-coordinate here, is coming from three different x-coordinates, here, here, and there. In some case, we may have just one crossing. Okay, in this case only one crossing, but in some other case I have multiple crossings. Here even more multiple crossings. Now if you have a one-to-one function like this, forward, and then I can always come back. X going to y, y is coming back to x. That return process is called the inverse function. So from x to y, original function, y back to x. That's the inverse function. And we use this notation, f to the negative first power, but we do not read it like that. We read it f inverse. The inverse function of f. And that's basically coming backward. X is going to y, then y is coming back to x. So basically domain is pushed over to range, range is pushed over to domain, back and forth. So domain of f is range of inverse, and range of f is domain of f inverse. X is going to y, y is coming back to x, and vice versa. Same idea can be applied to graphs, and you're going to get a symmetry. You see? Y is going to x versus y coming back to x, vice versa. Now, let's look at the graph. If you have y equals to f of x and y equals to f inverse x, then if you fold over the graph with respect to the principal diagonal y equals to x, then please note that the x-coordinate axis is folded right onto y-coordinate axis and vice versa. Folded over. Symmetric with respect to the diagonal. Blue axis, x-axis, is folded over to red axis, y-axis, and vice versa. So x is going to y, y is coming back to x. That's basically what inverse function does. So the graphs must follow the same property here. Graph of the original function down here, blue. And then graph of the inverse function here, red. They're symmetric with respect to y equals to x, as you can see in this picture. Folded over, then blue graph will be folded right onto red graph and vice versa. y is going to x is going to y. That's basically the reason. Compositions of inverse function, oh, that's even simpler. X equals to y and y is coming back to x. So if I compose, it should come back to x. And also vice versa, if I start from y to inverse, y goes to x and then x coming back to y, so we get the original, same thing back again. Too simple. Not really worthy of any class time so far. And finally, we have some example problems that are worthy of some class time. Okay, let's go to the first problem. Find the inverse function and determine its domain. Sometimes finding inverse is hard. Sometimes finding inverse is easy, but finding domain is hard. The first problem is the latter. Finding inverse is not difficult. The domain may be a bit tricky. Okay, let's go here. How do we handle this? Y equals to some expression of x, and inverse function is backwards, so x equals to some expression of y. But then again, typically we want to express it at y equals something. So I advise my students usually start with switching x and y. Our textbook author does all the solution by x and then switch x and y at the very end. But I usually do it beforehand. Switch x and y first, and then solve for y. Okay, alright, start from here, switch x and y. Alright, we got the first expression, and let's solve for y. So square both sides, we have x squared on the left hand side, and right hand side, we just lost the square root. Okay, let's solve for y, so flip one to the other side, we get this third expression, and divide by 2, finally we have an answer, y equals 1/2 x squared minus 1/2. So here we have original function, and here we have inverse function. But then again, that's not the end of the story here. If you plot this graph, the original function, we have this kind of graph, and clearly this is one-to-one function. You can see that, right? Now, if you start from here, (1/2) x squared minus 1/2, clearly this is not a one-to-one function. So this one has no inverse. You see, given y coordinate value, we have sometimes more than one x coordinate value assigned, so we cannot go back. So no inverse here. Something is wrong. What's wrong? It's coming from the domain here. In this domain, x is greater than or equal to -1/2. That's rather straightforward because we have square root, and inside of the square root has to be non-negative. But here it looks like this is valid everywhere for negative infinity to positive infinity, but no, there is hidden restriction, hidden domain. Because if you take entire parabola, that's not one-to-one. Something is wrong. So how do you find out the domain? Remember? No, not this one. Domain of the original is range of the inverse function. Range of the original is domain of the inverse function. Okay, domain of the inverse function, we have to find the range of this original function. So let's go ahead and do that. Domain of the inverse is range of the original. So let's look up the range of the original. Y equals the square root of 2x plus 1 is square root function, so it's clearly greater than or equal to 0. So we have this, y is greater than or equal to 0. Now if I switch x and y, x is greater than or equal to 0. So here we go. That's the domain of the inverse function, from 0 to positive infinity. So for original function, the domain is -1/2 to infinity. -1/2 half to infinity. That's the domain. And for inverse function, the domain is 0 to infinity. Here are the graphs. Blue is the original, so negative 1/2 to infinity. And then red is inverse function, 0 to infinity only. Not the left-hand side. If I take the left-hand side, then the graph is no longer 1-to-1, no longer invertible, everything breaks down. So upon appropriate restriction, we have appropriate symmetry here, symmetric with respect to the principal diagonal. Everything fits. Okay, tricky? Yes, indeed. Yes, indeed. The chance that you're going to meet this kind of problem in the exam is relatively low. I do like to write some inverse function problems, yes, but the domain part, that's too tricky. So the chance is not zero, of course. I can write, and I have written before, but if I do write, it must be intended as exceptionally tough problem. Okay, we went through inverse function in its domain, and I don't think I have enough time to start B. So let me mention a little bit about C, and then just talk about B in the separate video. Okay, all right, let's go to C. We have this quadratic function, and we have this restriction, x is greater than or equal to 2, or equivalently speaking, x belongs to 2 to infinity. So that's the domain here. And why is this so special? Well, if you convert this one into vertex form, you will understand. Oops. If you change this into vertex form, then let me see. Oh, no, where is the vertex form? Oh, we have vertex form here, okay. Okay, I switch x and y, and then rewrite this into vertex form. Yeah, okay, right here, vertex form. I switched x and y, so vertex form. And then you can solve it. So flip 5 to the other side, and then take square root. So we get square root function, but we have plus or minus square root. Which is it? And that's related to the domain and range, so it'll turn out plus square root. Not this, but it'll have to be plus square root. The detail is left to the student. It's rather tricky. So if I take only plus square root, only 2 plus square root, that one, and this is this red graph here. And then this one here, restricted to greater than or equal to 2, is this part of the parabola. The other part is thrown away because if we have the other part, then it's no longer 1-to-1, so no inverse function. So I have to restrict my domain. If I do that, then we have inverse function, and we have this principal diagonal and the symmetry and everything. Too tricky? Yeah, I can see that. That's why I de-emphasized this in gray. I said even this is a little bit exceptional if I put domain in there, but this one is kind of outrageous. The reason I covered it anyway, other than a little bit of extra time, is because this problem did appear in our textbook, believe it or not. Okay, so much for elementary, and let's discuss one last problem in the next video.